this is going to be the last 15 minutes. Yours is simpler than the one from the previous section. So you actually don't need a calculator. That one, the message that I sent out yesterday was for the previous one. A simple check on your understanding of those, one of those random variables, nothing more. Almost the same as homework questions. So your case, I think it should be a breeze. So what we did yesterday, we defined this continuous random variable, and it's the relating or associated the density function. And then we went on to discuss the thing about this so-called the cumulative distribution function, defined to be the derivative of this CDF. Turns out to be the same as the probably density. So that's one of the things that we derived yesterday. So we build on these the results from yesterday, and then go on to figure out what's the expected value and variance of this continuous random variable. So definition, there's a x which is known to be a continuous random variable, such that the value taken by x is uncountable. And we further introduce this PDF of x, which is denoted by this little f. Then its expected value of x is defined to be this one. First, come up with this product of a variable x and its PDF, and then you're supposed to integrate the product over the range which this x is defined for. So if you recall what we did in the discrete case, you see that there's such a close analogy between those. So let x be and the expected value where is P probability mass function x. So that's how we define this expected value in the discrete case. And if you compare the definition for the same expected value for the continuous one, you see that there's such a close analogy. The only difference, two differences, is that first, you need to replace that PMF by this PDF, because we have a density function, not mass function for the continuous case. And then what's even more is that the summation goes away, and then you have to replace it by the integral, because of the relation between the Riemann sum and integral that we introduced yesterday. It's nothing but an approximation. Other than that, it's basically the same. So only the PDF takes place the PMF, and then the integral should be used instead of the summation, and the rest of them should be the same. So the first step in computing any expected value of continuous random variable is to figure out what this PDF is. Some examples. First one is this one. X is known to be some continuous variable, random variable, and its PDF is given. So it's now simple because you don't have to derive it. But then the range is defined to be bounded between 0 and 1. So within this range, whenever the x takes any value between this 0 and 1, PDF is known to be twice the value of x. But outside this range, there's no probability mass. It's just a 0. And given this PDF, you're supposed to get the value for this expectation of x. Do it now. How'd you get it? So simple. So use the definition which was given by here. And if you do it, you get this. So since this case is PDF given, is given, it's just nothing but that you need to record this definition of expected value and then just to compute it. And that's all you need to do. One thing that you might have to pay some attention to is the range. This is not just over any numbers, any real numbers. In fact, if you just plug in any real numbers, you first have to divide into these two different cases. But no matter what the value for x is outside this range, the mass function is 0, so you don't have to think about it. Only pay attention to this small range. So range for x for this computation should be running from 0 to 1. then the probability density function first, and then you have a further x on top of it. So the product of those two should be twice x squared. And then if you integrate it over the range, you obtain the 2/3. Like I said, if this is your first time to be exposed to this computation involving integral, the general rule is the following. If you already know how to manipulate this one, you're fine. But in case you haven't done anything like this one before, so raise the variable to the power of a, and then if you integrate it, add 1 to the exponent, and do the same thing for the exponent of x itself. And if you apply that to that specific example, the constant is not going to do anything. It's just a fixed number. So either you put it here or just pull it outside, same thing. So if you first do that, it's this one. First go for the definite integral to the indefinite integral part. That's going to be 1 plus 2. And do the same thing for the exponent, 1 plus 2. Just need to plug in 1 and 0 into x. And if you do the computation correct, you get this is nothing but 2/3. And that's how you get the same number. Simple practice. So for this one, you just need to remember some of you might have done this one before, others might be the first time. So. This definition of expected value won't be given because it's just way too simple. Don't expect me to provide this formula here. So nothing like this on the exam. You just know how to do it. You should know how to do it. I mean, that's what I mean. Okay. And the structure of this density function can be complicated, but here it's very straightforward. The value of x itself and then just twice of it, but then you can introduce some sort of like a nonlinear function so that the computation becomes non-trivial at all. That's one extension. It's a possible extension. Okay. Done? All right. The second example, this one is non-trivial because what's happening here, the next example, the structure density function is actually simpler compared to the first. It's just one fixed number 1, and then this one is the case between 0 and 1. So if x becomes anything below 0 or above 1, there is no probability density, but only within this range. So I'm supposed to take fixed number 1. This type of density distribution of random variable is called a uniform random variable, which we will formally introduce when you come back next Monday. But for now, we just say that the name of this type of density is called a uniform density. Doesn't matter what we call it, we just know what it is. And given this probability density of this x, this time we don't compute the expectation of x, we are supposed to get the expectation of exponential to the x. So that's the crucial difference. If it's just the e of x, it's just the same as before. But now you deal with the function of x, not just x itself. So getting the expected value of this function of x is quite different from just simply getting the expectation of x. So how do you go for this one? You all know what the exponential is, right? So some natural number, 2 point something something. And then you use x as its exponent, not the base. So first down here at e as a base, and then you raise it to the power of the variable x. And then the probability density is given for this guy, not for the entire function. And then you're supposed to get the expectation of the function itself, not x. How do you do it? Any idea? Well, what you have, you're given this definition. So given x, if we know the probability density function of x, which is this one, the formula dictates us that this should be the right or correct expectation of x. That's all we have. And now you have this e to the x. So what do you need to figure out if you still want to use this definition? You can start by defining some new random variable like y. So let y be e to the x. Right? There's nothing wrong with just defining it. Then what you need is the expectation of e to the x, which is the same thing as expectation of y. But then by this given definition, should be the PDF for y, not PDF for x. But do we have this one? PDF for y? No, we are not given. But we are not given, but we need it. Then what do we do? We derive it. We have to figure out what this one's are. So the whole question boils down to whether we can get this one or not. Probability density function of e to the x. Once we figure out this, and then you just go ahead and compute that integral. But how do you get the PDF for y? When y is defined to be e to the x. So y is there. That's what we define it. We only have the PDF of x, not PDF of e to the x. How to derive the PDF of y then? Out of nowhere. Well, so the general rule is if you deal with a continuous random variable, and for some reason, the reason here is you need to compute the expectation of this function of x, first get the CDF of whatever the random variable is, and then you extend it to obtain the PDF. So that's the general rule. But since both x and y are continuous random variables, and you need a PDF of y, the right place to start the whole thing is to try to get the CDF of y, and then you get the PDF. Because once you get the CDF, you can use this definition, relation between CDF and PDF. So CDF is here. Say that you obtain the CDF of y, which is this highlighted function. You can just simply differentiate it in terms of the function's argument, and that will just kind of basically give you the desired PDF of y. So the step is always, when it comes down to continuous random variable, if you want the PDF of the random variable, first get the CDF, and then use this relation between CDF and PDF to eventually get this right hand side, which is the PDF. Why CDF first and then PDF? You'll see why if you try a bunch of examples. Computation, that's much more feasible than the other way around. Because moving from PDF to CDF, you have to integrate it. That's usually harder. first get the CDF, and then we try to get the PDF for y. How to get the CDF for y then? Where do you get the CDF? Start from the definition, of course. Definition of the CDF is given somewhere here. So this is the way we define the CDF of x here, but we want the CDF for y. So by definition, so define this one to be big F sub big Y of y is a CDF for y. Defined to be nothing but the probability. And then y, we defined it to be exponential to the x. So that's just a notation. How we write this CDF function, the uppercase F sub the name of the variable y here. And then this one is defined to be nothing but the probability such that this variable y either equal to less than some number. And by that, so this one right here is the definition of the CDF. Okay? And the definition of y, we already did it. Defined it to be e to the x. Go back to the question. Now what? How do you move from here to get the CDF of y? Any idea? Well, you have an idea and don't want to say, that's fine. But if you don't have any idea, it's not good. But where do you go? I mean, to get the CDF for y here. What should be next? Well, go back to the piece that you got. The only thing that we know is the PDF of x. That's the only information that we can rely upon. There's nothing else. Which means that we have to relate this back to x in any way. Otherwise, we get stuck. So one way to express the whole relation in terms of x, if you take log of both sides, have this. How do you know that the equality is preserved there? How come you claim that this probability is exactly the same as that? I mean, if you forget about this probability outside, this statement here, how do you know that this one transformed into this one? If it's an exact equality, of course we have it, but there's an inequality as well. So if this is an exact equality, no inequality, then this one of course implies that. But if you include this inequality, still the inequality is preserved. Yes, it is, because the logarithm is a monotone function. If you know the shape of log, that's only increasing. So if you pick up any two real values, real numbers, a and b, could be the other way, such that a is bigger than b, but that doesn't really matter. Assume that a is less than b. If you take the log of a and log of b, that's here. So here's a log of a, and this is log, and here's a log of b. Whatever was bigger on the x-axis, the inequality should be the kept, preserved even after you take the transformation of this one, because this is only increasing. If the function is something like that, this relationship is not guaranteed to hold true, but this one here is guaranteed to be true because of this is a strictly increasing function. So it doesn't matter whether you list them or order them in terms of size on the x-axis, or after you transform everything, because it's just only monotony increasing. So that's okay here, because logarithm is only strictly increasing. Then we can simplify further, so there's no question mark. That's okay. Go ahead. What's this left-hand side? Log of e to the x. That's x. Yeah, that's just x. We still have a log of y. Now the same statement, now expressed in terms of x only. Now what? Where do we go from here? So again, we got the PDF of x. We can use this one. So PDF of x is given to be 1 only if x is bounded by 0 and 1 and 0 outside. You can just use it. And that's just a 1. Right? And if you forgot where we picked that one up, go back to the one of the application of this PDF. Go to somewhere. Yeah, right here. So anytime you have to compute certain probability involving this x, if you know the PDF, you can just simply integrate the PDF over the range to which this x belongs to. And that's just the 0 and logarithm of y here. And then the PDF is known to be 1 in this case. So the bottom end should be 0 because although it doesn't specifically say that what's the lower bound, but if it goes below 0, I mean probably the density function is 0 anyway. So integral doesn't really count. So we have to stop at 0. And then go up to like a logarithm of y. And then you're basically done because what's this? What's the value of this integral? Log of y, yeah, ln y. So that's the CDF. So this is the CDF of y. So step 1 is done. You got the CDF of y. Now what do you do? So eventually you want to compute the expectation y. You have the CDF of y. What's next? So erase all that. You got it, right? So you don't need these middle steps anymore. Only need the result to move on. So CDF of y is known to be log of y. Then what do we do with this? We get the PDF of y. But how do you get the PDF of y? Use a relationship between the PDF and CDF, which is this. Here it's given. CDF on the left-hand side, if you differentiate the CDF in terms of its argument, A in this case, but doesn't matter whatever it is, and then the result on the right-hand side is going to be its PDF. You want the PDF of y given the CDF of y, so you differentiate it. So if you differentiate the left-hand side of capital F sub y of y, which is a CDF of y, you get the PDF because of this. One of the things that we derived yesterday states that if you differentiate CDF, you get its PDF. But then what should be on the right? What's the derivative of logarithm of y? If you differentiate ln of y in terms of y, what do you get? 1 over y, exactly. Inverse of y, or reciprocal of y. It's just a property of logarithm. So if this differentiate ln of x in terms of x, you get 1 over x. If this is your first time to say anything like that, memorize it. It can save your life on many occasions. Especially when you take a course in macro theory and on economic growth. Take the derivative of this log thing all the time. So this is nothing but the result of that application. So now you have the PDF of y. What should be the last step? Go back to the definition of expectation. What else? Go back to the definition of expectation here. You want the expected value of y. Remove all that. Finally, expectation of y. Using the definition, now here's the big question. So that's the easy part. What should I write here and there? What should be the bottom end and top end for this definite integral? That's going to be the range of y. But what's the range of y? Range of x is between 0 and 1 in this example. Right? Range of x is given here. But what's the range of y? Anyone? Where does this y run? From where to where? So y is e to the x, where x is running between 0 and 1. The range of y is e to the 0 to e to the 1. So that, but this is 1. So the range should be 1 down here and e up there. So there should be exponential e. But then you have that PDF of y is known to be 1 over y, and you multiply that one by y itself, so this is nothing but 1. And if you integrate this one, what do you get in the end? E minus 1. Should be the final answer. You either do it that way or just go with the model solution, which is. So if you have to derive or obtain the expectation of certain function of original x, it's always 3 steps. Step 1, figure out the CDF of the transformed x, not the original x. So transformed x in this example is e to the x. So go for the CDF of this guy first. And CDF is given here. And then given the CDF of transformed x, you obtain the PDF of it, which is this one. And then the final last step is given this PDF of y, go for the expectation of y. Then you're done. Always 3 steps. Don't forget those steps. either on the midterm or final, save your life. Especially for the final. Every time I grade the finals, I just realize how many students forgot these steps and got lost in somewhere. But please don't do it. Plenty of practice questions will be given by the following homeworks, homework 4 and 5. And then after the midterm, we'll have a chance to go over the material and do more examples and more practice questions. So plenty of opportunities down the road, but I'm just telling you that this is important practice. Or there's a simpler way. If you don't want to do it through these 3 steps, not always, but sometimes it works. It's a much quick shortcut, and then the shortcut is given by the following proposition. So either you do it this way or use the following proposition, which is this. So again, if you recall what we did in the discrete case, we did something very similar. What we did is this. The proposition that we handled in the case of discrete one. Now it's a continuous case, so we have to do the integral instead of summation. So the key thing here is that this PDF is not the PDF of this g of x, it's just the PDF of x itself. And then nicely and quite conveniently, you can compute the expectation of this function of x still using the PDF of x. So there's no need to derive the PDF of g of x. So first define g of x to be y, and then get the CDF of y, and then get the PDF of y, in order to fill in that PDF of y in here. But what's nice about this proposition is that you don't have to do all that hassle. Just get the PDF of x, and then just use it here, as if it's the PDF of y. And then the computed expectation, integral, turns out to be actually the same, which is very convenient. How convenient? You'll see it if you try the same question that we tried using those 3 steps. Now under this proposition, just one line will does everything. Will do it everything. So this is the same question as before. Same PDF, same range. Outside this range, there's no probability mess. But then given this, you're supposed to get the expectation of e to the x, not just x. But then if you use this proposition, just one line does everything. So expectation of e to the x, integral, so integrand should be function itself. But then you don't need to derive the PDF of this e to the x, just use the PDF of x, which is 1. So it's just the same thing, whether you write it e to the x times 1 or just e to the x, then the range even stays the same because everything is in terms of x, between 0 and 1. But then this integral will nicely give you the exact same answer of exponential minus 1. Just the same thing as what we got right there. But see how many complicated steps you have to go through to get this answer. In comparison to just one line under this proposition basically deliver you the same answer. So how convenient this is. Simple way to double check whether you got the correct answer for the previous question or not. And indeed it's correct. Okay. Keep this one in mind. Save your time on many occasions. Not much to remember to begin with because we already did something similar in the discrete case. Just need to replace the summation by integral this time. Idea itself basically same. No need to derive the PDF of those transformation of the original x. Okay. Now, corollary. Corollary is some useful results out of some proposition or proof. Theorem, this itself, we don't have to prove it, but the result might be worth to remember. So here's what the corollary says. Assume that a and b are some fixed constants, and nothing but some numbers. But then if you compute the expectations of linear transformation, linear combination of this x, first multiply that one by the first number a, and then add up the second number b, and then take the expectation of the whole thing. Turns out to be the same as first compute the expectation of x, multiply a, and add up the same number. Did the same thing for the discrete case. But how do you prove this one? How do you prove this expectation? Turns out to be the same. Just assume that this is true. How do you prove it? If I ask you to prove, you see that this is nothing but some function of x. Should ring a bell. I mean, if you go back, the proposition says expectation of some function of x can be computed using this PDF of x itself. And this is no more than just one specification of the previous general function. So use the proposition. So if you use the proposition, so by the proposition, this is the same as integral the function itself and the PDF of x, not the PDF of the whole thing. Right? So that's what the proposition says if you go back. You're applying this one. You can expand it. Just apply this function to the first term inside, and then apply the same function to the second term inside, and just write that as two different factors. And then you can divide it into two different integrals. But then this a is just a constant, so this a can come out of this integral. And do the same thing for this second coefficient, which is b. You can bring it outside. What is this guy? E of x, expectation of x. By definition. If you forgot the definition, go back. Here's the definition. You see that the right hand side of that is the same as this. What about this guy? Use the yellow. Because it's the PDF. So it should be 1. Done. That's what you need. So that's nothing but E of A times E of x plus b. So on the exam, I can change this function. Here it's just simply a times x plus b, but I can write instead some different function of x, and then ask you to verify it, and you basically go through the same steps. And many other ways to ask basically the same thing. So do it now, because you have to do other things later. Don't delay. So that was the one application of the introduced proposition. Now you define this variance. Definition itself, so there's no difference between the discrete case and continuous one. So now you deal with this continuous random variable and the variance of x. Typical measure of how much spread and under this distribution is computed by this one. First, figure out the mean of x. So that's the expectation of x. Just a notation. Subtract that mean from x and then square it. Don't forget this part. And then take the second expectation of the whole thing. And this one is defined to be variance of x. Nothing new. Did it before. And even this alternative way to compute this variance stays exactly the same. If you don't like this one, computationally this is the second one is much more straightforward. First, go for the second moment of x. Do the expectation of x squared. And then subtract the squared value of this original expectation of x. Same thing. Whether you compute it this way or that way, will bring about the same answer. But most people go with this second, because it's easier to handle these separate expectations rather than put everything inside this big bracket and then just take the expectation of the whole thing. Mostly people do it this way. Nothing new. Given this, so given these two definition and the useful representation, we go for this first example of variance. PDF of x, continuous x is known to be twice x between 0 and 1 and 0 outside. Then the question is asking you to compute what is the variance of x. So if you go with the second way to compute the variance, first to compute the expectation of x squared, and then figure out the expectation of x, square it and subtract it, do the whole thing together, and then you're supposed to get the correct answer for that. And if you do everything correct, what you should get is this. So go for the second moment first, which is expectation of x squared. But then for this one, you again have to apply that proposition, because you don't want to derive the CDF and PDF of x squared all over again. You just use the proposition which is already given to you. still it's okay to use the PDF of x, not the PDF of this x squared. Figure out this, straightforward integral. That one turns out to be half. But then you turn to the expectation of x. This one you have to compute it. This is not assumed. You actually have to go through the definition and then just make sure that you get the same answer. Then square that and subtract that from the e of x squared, and eventually it will give you the final answer of variance of 1/18. So this part, verify at home, whether you still get the same answer. One last thing. You should be ready for the quiz. I mean, this quiz should be a piece of cake. If you have a trouble with this one, give me a break. Done? So last one is this one. Second corollary. Did a similar thing for the expectation of transformation of this x thing. Now you're dealing with the variance. A and B again assumed to be some fixed numbers. And then first define linear transformation of this original x. Previously, if you take the expectation of this combination, what you get was this one. A and B still alive, and even the position doesn't change. Multiply A by this e of x thing and then add up the second number. But then if you do the same thing, take the same linear transformation, now you turn to variance of it, some change occurs. The variance, the change is this addition disappears. Only the coefficient survives, but you have to square it. And then multiply that by the variance of the original x. How do you verify this? That's the last thing. Think about it like 1 or 2 minutes and then we can discuss. Try yourself how you can verify this. At least to think. There are two ways. One way is longer, and second way is quick. Fairly simple. So in the case of expectation, we took the proposition and just applied the proposition to prove it, but there's no proposition to use for variance. Well, stretching is good, but I ask you to think about the answer. Talking to you. Stretching is okay, but I ask you to think about the question first. Nothing wrong with the stretching. It's good for your health. It's not a bad idea to relax before the quiz begins. Talking about the midterm exam, there will be 3 parts. I usually make the midterm at 3 questions and final add 1 more and 4. These are not just talking about 3 separate questions. It's just like they're like a series of sub questions for each. Like part 1 usually have like 6 sub questions. There's no coherent theme for this first part, like questions 8 through F or something. So that's 6 of those. And these sub-questions are not related to each other. One of them could be like, I don't know, define the compute the expectation of certain variable. Next question might be asking you to come up with answers for those combinatorics questions, counting. Others might ask you to what's Bayes theorem, something simple. Something that doesn't require you to think about like 5 or 6 different lines or anything. Like 1 quick line of answer just does everything. So that's usually put into under the first part. Part 2, there's one topic. So second part could be like all about, say, Bayes theorem. just an example. I don't mean that this is the actual one. So the topic for the second part is just the base theorem, but then there's like a series of sub-questions under which. So it could be like another 4 questions. But this one is somewhat different from the first part because these are all related to each other. If you don't know answer to the part A, you probably get stuck with the rest of them. So these are sequential. But these are not. They are separate. The fact that you didn't figure out the answer to A doesn't mean that you have the same trouble to B, because those are completely different questions, but these are all related. And then usually the longest part, longest one goes to the last part, part 3. This one could be like a probability density function or CDF or computing expectation variance and everything. It could be like a, I don't know, A to like a E or something. So there's 6 of them. 4 of those, that makes 10. Another 5, so there's a 15 sub-questions clustered under 3 different groups. You have 1.5 hours to handle those. Traditional students have no problem, because I adjust the difficulty level. 1 hour and 30 minutes is just enough to finish it. You won't be able to leave early. You can leave early if you want. I mean, you can just do all the questions in half an hour and then go. But if you are serious, want to give your best to it, usually 1 hour and 30 minutes is just enough. The second page of the exam is a formula sheet. Whatever formula you might be needed to use to answer these questions, don't have to memorize them. I'll give them to you. And then not for this one, but for the finals, you have to rely upon those distribution tables. Copies of those distribution tables will be also given. So if you attend the review next Tuesday, you have a much clearer picture of what those actual exams will be like. Because by that time, I'm certain we're done with writing it, but not now. But that's the typical way to structure the exam. You have to take in mind before. So getting back to this one, how do you do it? The quicker way is using the definition. So by definition, if you take the variance of the whole thing, so this is defined to be that's by definition, which we introduced right there. So put the into the place of x is the a times x plus b, and then put the expectation of that into the place of this mu, and you see the right hand side. Now what? Corollary number 1, you apply that. This is a corollary number 1, which applies to this part. So if you apply the corollary number 1, what you're having is right? But then you see that there's a same b here, same b there, but you have to subtract it, so they kill each other. And another thing is there's a same a, but then you times x, but then when it appears again, you have to multiply this one by e of x, so you can factor it out. So if you factor that one out, but then there's a square on top of it, so you first write a squared. X remains inside. You have to subtract e of x. And this a squared is just a number, so you can pull it outside. And if you do that, but then by definition, what's remaining here is nothing but the variance of x. Done. Pretty simple. And it requires to take 3 lines, 1, 2, and 3. But if you do it in a longer way, you still get the same answer, but it's just more tedious. So try to do it in a quicker way. Anything that so the midterm, in terms of grading, the median score is a key. If you stay above median, I traditionally assigned either A or A plus. So roughly speaking, like a half of the class member finished with either A plus or A. So the median is like if you stay above the median, whether the exam is easy or hard, it doesn't matter. It's all relative. So you should be okay. But if you're just around the median, depending on the exact distribution, your grade could be like a B plus or B0. But if you stay below the median, that's not good. And I occasionally assign Fs, but those are like a rather infrequent because I mean some students never bother to show up in class and they never take the exams and never submit the homeworks in the past. So other than those rare occasions, usually you will be able to finish this one with like some grade, at least the B plus or B0. But definitely I need your help or cooperation on that side. Any other things about what we did today or? Clear the desk. You have a 15 minutes for this one. It's nothing computational. It's just a simple check on your understanding of one of those variables. So it shouldn't be 15 minutes should be long enough, I think.